So I was discussing about the absorption and optical absorber and the optical amplifier, both in the pictures of wave and particles. Okay, so I think I was here last time that I was discussing, if there's an absorber in terms of its if you want to see the picture in terms of microscopic view, that how the absorber works. If there are some number of photons that comes onto it, this represents the energy levels of an absorber atom, and most usually the atoms are on the ground state, the lowest energy state. And what happens over here is that if these photons have the energies which is equal to the difference between E2 and E1, in that case one of them will be absorbed. Okay, so and as a result of absorption, the electron will go in the upper state. So that means the initial intensity of the light will be dropped, and this you see in this graph of intensity versus frequency. Whenever there is this photons which is equal to the energy difference between the medium, you will see a dip when the frequency of the incoming photons are equal to the energy difference between these levels. Okay, so as soon as you see a dip, that means there is there are atoms in the medium that absorbs that frequency of photons. Okay, so you have certainly know which atoms are in the medium, or which photons are absorbed in the medium. Okay, which frequency photons. All right, so I mean, this is the wave picture. Of course, the wave picture is just, you will see the decrease in the amplitude. In the particle picture, in the photon picture, you will see the decrease in the number of photons. Okay. So, in fact, another name for the absorption is, in fact, if you have lots of atoms which are on the ground state, and if you send just right frequency, which is equal to the energy difference between the levels, the situation of that absorption is called the stimulated absorption, because already there are many electrons, many atoms in the ground state, and you just send the photons, or the energy of the incoming light, which is right equal to the energy difference, and the process is called stimulated absorption. But if you ask yourself that what happens afterwards to the atoms which are excited to the higher energy level, they will not stay in this excited level forever. Maybe I told you this before, and there is certain time of duration that these electrons, excited electrons, will live on the upper level, and usually this is in the order of nanoseconds. After some nanoseconds, these electrons will naturally, spontaneously decrease again to the lowest energy level, because this is a common principle in physics, that if there is no any forbidden case, all the systems in physics tends to be in the lowest energy state. So by following this principle, the atoms will not survive in the excited level, and they will drop their electrons to the lower energy. What happens when the electrons drops to lower energy? Since they lose energy, and that loss of energy will be radiated as photons of that frequency that equals to the energy difference between these levels, equivalent frequency, and these photons will, if you ask in which direction they will radiate, usually they will radiate in any direction they want, and it's spontaneously they might emit in any direction. Okay, so this is called the spontaneous emission. I mean, if you have excited atoms which are on the higher energy level, these atoms will eventually drop to the lowest energy level, and by dropping these electrons to the lower energy level, the electrons lose energy, but this loss of energy creates photons of the frequency which is equal to the energy difference, and these photons, if these photons radiate in any direction, okay, there is no any preferred direction, then the emission is called the spontaneous emission. So you can observe this process in a vapor cell, that you send some photons which you can vary their frequencies. Okay, you may have some variable wavelength laser or some light sources which has many different frequencies that you can control with certain knobs. When you change the knob, you change the frequency of the photons that you send to a vapor cell. That vapor cell means that there are atoms that can be excited by the applications of incoming light, single wavelength light, but you can change the wavelength anyway. And this is the detector. If the detector detects the intensity which is less than the incoming intensity, that means there is certain absorption process over here. Okay, and well, if you want to ask yourself that what happens to the loss of intensity, because you send intensity, larger intensity, but you detect lower intensity, well, since some of the photons will be absorbed by the medium atoms, and these medium atoms will drop their energies from excited to the ground state energy level for a while. After they absorb, they will radiate some photons in any direction through this vapor cell. Okay, and this is the signal that comes from this detector, because when you send some intensity of light which is not equal to this F12, the energy difference between these two levels, there is no any absorption at all, and whatever you send, you will detect the same intensity in the detector. But as soon as you come towards this spatial frequency that is equal to the energy difference, you will see that some portion of the intensity will drop, because they will be absorbed by the atoms in the vapor cell, and they will again re-radiate these photons in any direction. Usually it takes a certain direction of photons, but it radiates the photons in any direction. That means you have a spontaneous emission. Well, why I'm telling this, because there is another type of emission which is unique, and in order to make a difference from that type of radiation, I have to tell you that this spontaneous emission is a special type of emission. And the spontaneous means you take the energy of photons in a certain direction that comes onto you, but you absorb the energy and you re-radiate these photons in other directions, in any other directions. Okay, other than the incoming direction. All right, so what you see in this picture is that as you can see, it's an amplifier, but the thing is that you send a single photon which has a frequency which is equal to the energy difference between these two levels, and you have a single photon that comes onto this atom, and the atom originally is not on the ground state, but it's on the excited state level. So what happens when this photon meets this excited atom? If the photon has the frequency which is equal to the difference between these energy levels, what happens is that you might think that, well, this electron will absorb this energy of the photon, and it will go even higher energy level, because it absorbs this energy. It may absorb this energy. When absorb this energy, it will tend to go at a higher level, right? This is what you might think. But in fact, this doesn't happen that way. What happens is that as soon as this electron, excited electron, sees this incoming photon, it drops its energy to the ground state. Well, while dropping its energy to the ground state, of course, since it has excess energy coming onto the ground state, what happens to this excess energy? It will produce a second photon. So you send a photon to excited atom, you get two photons and a ground state atom. You start with excited atom, you're left with ground state atom. You started with single photon, you end up with two photons. There is no any energy conservation violation. Energy conservation holds, no problem in that, because you have this energy over here and this energy over here, and only this energy turns out to be a second photon, and this first photon is preserved. There is nothing happening to the first photon. Okay, first photon continues motion, but what it does, it stimulates the electron, which is originally in the excited level. It stimulates it, and it forces it to drop. Well, you may ask that how the electron senses this photon. Well, we don't know. We don't know how it senses it but what we know is that if it falls onto the electron, this happens. Okay, 100%. This happens 100% time. Okay, not most of the time. This happens as soon as the photons are just on the way of the electron. The atoms does 100% this behavior. This is called stimulated emission. Why? The first thing is that if you repeat this process many times over, you might notice that, well, okay, we had this excited atom, but the atoms goes into the ground state level, so it must radiate one photon, but this photon might be coming in any direction, right? It should come in any direction. But if you repeat this experiment many times, you will observe that this emitted second photon will always be emitted in this preferred direction of the initial photon. Okay, so this is strange behavior. Normally, what you will expect is that the electron will drop to ground state, and it will emit a photon in any direction. The photon will come in any direction. But this doesn't happen so. If the change of the energy level of the excited electron is triggered by this photon, the photon that comes after this change of the level always in the direction of the original photon, and it always will have the same phase with that of original photon. It will have all the properties the same as just copy of the first original photon. I mean, the secondary photon that is created by this this change of energy level of the electron will be just a carbon copy of this original photon. It will not go in any direction, but it will be just carbon copy of that photon. Whatever that photon goes in the direction, its original direction, the second photon will always be the same direction as that of the original photon. And this directional behavior, unexpected directional behavior, is called stimulated emission. Okay, and remember that, sorry, this is the spontaneous emission. You see, photons comes in any direction, but over here, photons, the created photons goes with the same direction with the incoming photon. Okay, there is difference. Both are the emissions, but this one is spontaneous emission and this one is stimulated emission. Okay, in fact, this is the process that creates the laser. Okay, so okay. And okay, if you just prepare some setup that has many atoms, like atoms in the excited levels, and you send some photons which is just equal to this energy level, the frequency which is equal to the energy level, you will always observe the created photons coming out with the same direction as that of original photon. And when you look at this process in the detectors, if you have a variable frequency photon generator, and when you change the frequency of the incoming photons, right, just which is equal to the energy difference, this F12 is just E2 minus A1 divided by H, what you observe this process, okay? What you observe this process, since you send some intensity, but you observe a larger intensity, you see over here, this is the original intensity, but you get enhanced intensity right at this frequency, which is equal to the energy difference. Okay, and you know, this is the photon picture, and this is the wave picture. In the wave picture, you see is just the increase of the amplitude, but in the photon picture is what you see is just the increase of number of photons. Okay. All right. Okay, so this is stimulated emission and this is spontaneous emission, just next to each other, but they are different. Spontaneous emission occurs if you start with some number of excited atoms, but there is no any surrounding photons or coming photons onto these atoms, nothing, but you have started with the excited photons, and eventually in the order of nanoseconds, these electrons will drop to ground state. They will radiate photons in every direction, possibly in every direction. But in here, again, you have some initial excited atoms or electrons in the higher energy level. But if you send some extra photons right onto these atoms, okay, which is just equal frequency, which is equal to the energy difference, what you observe is that, again, you will observe a radiation, increase of the radiation, but this radiation comes in a direction which is just equal to the original incoming photon. Okay, if there are original incoming photons, the created extra energy, extra photons will always go with the same direction as that of this original photon electron. In that case, we call the emission as the stimulated, but this one is spontaneous. Okay, so this is the difference. Okay, this is the difference between spontaneous emission and stimulated emission. And spontaneous emission cannot create laser or lasing. The ones that creates lasing are the stimulated photons, stimulated emission photons. So in order to start a lasing action or a laser light, you must produce your photons by the process of stimulated emission, not the spontaneous emission. Spontaneous emission creates light, but this light will just diverge, will radiate in any direction. All right, but stimulated emission is always collimated. They always comes with the same direction. Okay, so that's that. I mean, this is the main difference between two types of lights, and you just know that laser light is nothing but stimulated photons, but other light is just spontaneous emitted light photons. So we have this, of course, in this picture. What you see is over here. In order to have a extra energy created from your system, if you want to create extra energy, because you pump somehow your your atoms into a higher energy level, and you just give some energy, but if you want to have more energy, more photons, you must have this condition satisfied. You must have more number of atoms which are on the excited state in compared to the atoms on the ground state. Otherwise, your system will act like an absorber. Okay, if you have some atoms which are on the excited level, but if you have more atoms which are on the ground state level, and if you send some light on this system, okay, first of all, I want you to tell you that every circle over here, every electron, these blue circles are representing electrons. And for example, if every electron represents one single atom over here, if this electron is at the energy level 2, this represents an excited atom. And if the electron is on this level, one electron represents the atom on the ground state. But what you see over on here is 1, 2, 3, 4, 5, 6, 7, 8, 9 atoms. Only 3 of them, over the 9 atoms, only 3 of them is in the excited state, and only 6 of them on the ground state. If we have a larger number of atoms which are on the ground state in compared to the excited state, your system acts like an absorber. You will never increase the number of photons from this system, even if you just send some photons to produce some kind of stimulated emitted photons. You will not be able to do it because there are more number of atoms which are on the ground state. So these will absorb this incoming light more strongly than these will absorb this to emit extra photons. So net process over here is just absorption. If you send some intensity of photons which are equal to the energy level, the frequencies are equal to the energy difference between these, you have a net absorber over here. So the condition that this N1 and N2 represents, N2 is the number of atoms which are on the ground excited level, and M1 is the number of atoms which are on the ground state. If M1 is larger than N2, you have an absorber. But if you have the other way around, if you have N2 is larger than M1, then in that case you have a net gain. If you send some initial photons, initial light, which is just the equal frequency to the difference between the energies over here, you will produce a amplified light which is just equal to the energy of the incoming light and larger in amplitude, or in terms of the intensity. It will be same direction, so it will be stimulated light, stimulated photons, and as long as you have N2 larger than N1, and you have in this case what they call is population inversion. So population inversion is one of the condition, must condition. I just forgot to hit the record button. So the population inversion is the must condition to produce stimulated photons, which is nothing but the photons for a laser, for lasing action. Okay, so this is the must. I mean, this is one condition that you must have population inversion. But you might ask yourself that, okay, how can I get the population inversion? How can I get normally all of the atoms in a medium? Most of the atoms are going to be on the ground state, and maybe 99% of atoms will be on the ground state. How can you make them on the excited level? What you do is just give some energy. This might be electrical energy, well, mostly for semiconducting laser, or for gas lasers, for solid state lasers. What we do is, this is why lasers work by batteries. Batteries provide some energy that the medium atoms go from ground state to excited level, and they take energy, electrical energy, they go over here, and then some photons will start the stimulated emission action. Okay, and these photons will be used many times over. If you put over here and over here 2 mirrors, because when you start this action of stimulated photons, if you start with one single stimulated photon, when there is nothing else, which goes in the direction which is perpendicular to the surface of the mirrors, this stimulated photon will bounce back and it will come to the one of these excited atoms, and it will drop 100% all the time. It will drop one of them to the ground state. There will be 2, and these 2 will again reflect back, come to the same medium, and these 2 will drop 2 more and becomes 4, and these 4 will again reflect back from the mirror over here. It will come to the same medium again. This 4 will be 8, 8 will be 16. So each time the number of photons will increase geometrically, right? And for a very short period of time you will reach, by the way, in the meantime, when they drop these atoms to ground state, these ground state atoms will again go to excited level by the action of this electrical energy. Okay, as long as you provide electrical energy, when the atoms comes to ground state, because of this energy, extra energy, they will go again up in the higher energy level, and as soon as they reach a higher energy level, if there is again a photon that meets with this atom, it will drop. So this will continue, this cycle will continue forever and forever, over and over, as long as you provide the energy forever. This will go over and over. So exponentially the number of photons will increase in between these 2 mirrors. Okay, this is your optical resonator, you remember? Your optical resonator becomes, this is the resonance case. This resonator will produce the amount of photons which is going crazy and exponentially increasing its number of photons in a very short period of time. So whenever these number of photons or intensity of photons inside between these 2 mirrors reaches to some level, then one of the mirrors will act like half transmitting mirrors, let go these photons through the maybe 30% transparent mirror. So in that case, one of these mirrors will be transmitted some portion of the light inside the resonator, inside the optical resonator. For example, if there are 100 photons, this mirror will let only 30 of them each time. We let it go, but these photons will be created cyclically over and over. So whatever the number of photons inside this between the 2 mirrors, only 30%, if you have a 30% transparent mirror over here, one of them one of the mirrors. 30% of light will emit through this chamber, and it will be used by the output intensity, output light of a laser. So this is the way. This is the way how the laser works in short. So the question that how to make an optical amplifier is that certainly you must have some medium, and this medium must be pumped by some extra energy. And in the case of semiconductor laser or laser pointers that you use, this is done by battery, or this is done by the outlet electricity from your laboratory or whatever, electricity. And this electricity just pumps the ground state atoms into excited levels. This pump should continue until you have this population inversion realized. If you have certain amount of medium atoms between these two mirrors, you must at least have more than half of these atoms on the excited level. So once you reach half of them on the excited, more than half of them on the excited level, then you get the population inversion. But one thing is that if you ask this question to yourself, if you have only two-level atom means that one energy level is the ground state, this is the lowest energy, and the next energy level is just the excited level, but there is no any other excited energy levels. Well, there is no such an atom, but suppose you have such an atom, only two energy levels. Well, if you have only two energy levels, will it work? The question is, will you have an operating laser by just using some medium which has only two energy levels? Well, the short answer turned out to be no. You will never have a working laser if you have some medium or atoms with only two energy levels. One is ground state, the other one is excited level. And the question is why? Why you cannot operate such a medium as laser? Okay. Well, if you think really, carefully, or if you think long enough, I don't know how much time that you need to find this, but as soon as you have some atoms which are on the ground state, I told you that some of these atoms will, some of these electrons will only be on the excited level on the order of nanoseconds, and after that they will drop eventually. So they will drop eventually, they will emit, but this pumping process is continuous. So even if they drop, they will eventually go up on the higher level again, etc. But the thing is that this pumping process will never create a population inversion. If you continue this pumping process, even if you increase the pumping intensity, even if you increase the amount of energy or electrical energy more and more, you will never reach the number of photons which are on the excited level larger than the number of photons in the ground state. Why? Because if you reach this number of, initially of course the number of excited levels are going to be smaller than this one, so your system will act like an absorber. But once you reach these levels are equally populated, your absorber will never reach to a amplifier, because when you have photons coming and going back and forward in this chamber that you have these atoms or gain medium, your atoms will have equal chance of absorbing the incoming photon and equal chance of dropping one of the atoms from the excited level to the ground state. So suppose you have an incoming photon, and this photon has just right the frequency, which is equal to the energy difference between these two levels. And so decide what happens if this incoming photon will be dropping one of the atoms down by creating a stimulated emission, or it will absorb one of the atoms from the ground state to the upper level. Which one will work? Well, once you reach this equality, these photons will be 50% be absorbed by the ground state atoms, and 50% will be absorbed by the excited level atoms. So half and half. So it will never change this number. It will never create a difference between N2 and N1. N2 and N1 will always be the same, equal to same. Even if you increase the pumping ratio, this will never change because you have equal amount of probability to absorb this extra photon by the ground state atoms or by the excited level atoms. So if you have equal chance, then you wouldn't expect that this N2 will becoming larger than M1. Okay. You reach this level, then you stay there forever. Okay. So if there is no population inversion, there is no gain. If there is no gain, there is no lasing action at your hand. So that's why we cannot have lasing if you only have two level atoms. So that means in order to have a laser, you must have at least 3 level atoms, okay, in your gain medium. And what happens in your 3 level atoms? Suppose you have these 3 level atoms and you have this ground state numbered by 1, first excited state numbered by 2, and second excited state numbered by 3. This is the highest energy. E3 is higher than E2, and E2 is higher than E1. So you might ask yourself that, okay, you can always pump this. You can always adjust your pump so that your pump takes the ground state electrons to not 2 but to 3. So you give a larger energy, larger than this difference, E2 minus E1. In fact, you give just equal energy, which is equal to the difference between E3 and E1. In that case, you pump the ground state electrons to third energy level. Third energy level, if you just send some energy enough to take the ground state electrons to the third energy level, that's what the system do. They will go up to the third energy level. They will not go to second level. Okay, if they have enough energy to reach 3, they go there directly. They go directly to 3. And you might think that, well, maybe they go first 2 and then to 3, but this never happens. Okay, this is forbidden in quantum mechanics. And don't ask why. We don't know why, because electrons act like this way. They don't want to do these intermediate steps. You might think that they will first go to 2 and then from to T, but this never happens. Okay, they will always be populated from 1 to 3, if and only if you provide this energy difference in the pump. Okay. Well, okay. And the other thing is that, well, what happens to the atoms in the third energy level? Well, you might think that in the third energy level, the atoms may go down to 2 options may have, you might think, they may go down directly to 1, or they may go down to 2. Okay, so there are two ways. You might think that, okay, maybe half of them will drop to 2 and half of them will drop to 1. Well, what happens usually is that they will first drop to 2. They will not drop directly to 1. Okay. So you might think that, you might ask why. Well, this is another quantum mechanical effect. These transitions, when have more than one option to go from a higher energy level to lower energy levels, if you have more than one option, then electrons will choose the one which is a allowed one. Okay. So what I mean is that if you have two options, then if you're an electron, if you have two options, then you will be acknowledged that, okay, you have one allowed transition and the other transition is not allowed for you. Okay, this sounds crazy, I know. Well, this is called allowed transition and forbidden transition in quantum mechanics. In order to change for an electron its energy level to the lower energy levels, it chooses the one which is allowed. What I mean by allowed is that, for example, over here, this second energy level for this electron is allowed. And the third energy, the first energy level, ground state energy level for this electron, which is originally in the third level, is not allowed. Why? When a transition to become possible or probable, we also look at another state of the electron at these energy levels. Okay, and this state is called spin state. Maybe you heard. Electrons not only have their energies in an atom, but they have their spins. Electrons have this quantum mechanical property, which is called spin, and spin has no any counterpart in classical physics. Okay, spin is completely a quantum mechanical property. We cannot understand in terms of classical arguments. Well, there are resemblance that why do they call spin? Because electrons act like they are spinning. What I mean by spin is like rotating, spinning. Electrons are such a particles that they just act like they're spinning. Really, in the literally speaking, they act like they are spinning particles. How do you understand that they have spin? If some charged object is spinning, then it is producing some kind of current, right? Because if there is spin and there is some kind of motion of the charges, and if the charge moves or spinning or doing some circular loop, it produces a magnetic field. Okay, and then in that case, if the electron is spinning, it acts like a magnet, right? Because if it produces a magnetic field, it acts like just a magnet, usual magnet at your hand that you play with every day. You play with the magnets, small pieces. You can always find around. These magnets have north and south poles, etc. And just like this, electrons have act like south and north poles. They're acting like they have north and south poles. What I mean by the electrons have magnetic moments. Magnetic moment means electrons are act like spinning particles, act like spinning charges. So that's why we observe their spin effects when they pass electrons through some magnetic field. Some of them will deflect in the upward direction, and some of them will deflect in the downward direction. And that means some of them rotating in this direction, and the other one is rotating in the other counter directions. So yeah, this is it. I mean, whatever. The electrons have spin. I mean, so this is the observed quantity. So if the electrons are spinning, then when they go to this energy level, for example, this energy level states that, okay, on this energy level, the electrons can only come to my room from the third energy level. Okay, and this one states that, okay, if there is electron coming onto my level, then my these electrons must come from E2, because E2 energy level just matches to the spin state of the electrons in my level. So what I mean by is that electrons in the third energy level may not go down directly to the first energy level because of this angular momentum law, or the spin law. The spin law, just tells you that these electrons, third energy level electrons, can only go to the second energy level because the spin or spin angular momentum will be conserved, just like energy conservation. And then afterwards, after they come from E2 to E3, then they can go to E1. So if they want to go E1, they first have to go E2, then from E2 they go to E1. This is the way. And these are the transition rules, quantum mechanical transition rules. Okay, so that's that. I mean, so every time that electrons loses its energy, it will produce photons, right? When electron, which is on the E3, when it goes to 2, so since it drops to 2, it will radiate a photon. And also from 2, it will go to 1, it will again radiate a photon. So which photon will be lasing photon? Okay. So it turns out to be that as soon as if you look at these energy levels, as soon as your pump starts, as soon as the electrons go to third energy level, if you think that this 3 to 2 transition will produce your laser, because as soon as the pumping starts, there is no any photons in the second energy level, but as soon as you start this pumping, there will be some photons in the third energy level. And when there is some photons in the third energy level, as soon as only one single electron will go to the third energy level, this N2 larger than N3 larger than N2 condition satisfies right on. Okay. As soon as you start pumping, you satisfy the population inversion condition. Why? Because at 2 there is nothing. So literally N2 is 0. But since pumping is there are photons, so electrons always in the third energy level. As long as this pumping is going on, there will always be electrons on the third energy level. And on the second energy level, there will be very, very few electrons, because the other thing is that electrons, when they go to E2, they will not even survive to stay in E2 in nanoseconds. They will almost immediately drop to E1. So their lifetime on E2 is much, much less than their lifetime on E3. What I mean by lifetime is the amount of time duration that the electron will stay on this energy level. So if you have such a energy system, such a 3-level atoms, then this can produce laser. Okay, so 2 energy levels may not produce, never produces laser. Only by using 2 energy levels you cannot create laser. Okay, and that's why do you think so? Because only with 2 energy levels you never reach the population inversion condition. And what is population inversion? You must always have higher number of higher number of atoms which are on the excited level in compared to the ground state level of atoms. You must always higher number of electrons or atoms on the excited level than in compared to the ground state level. This is called the population inversion, and this only be satisfied only if you have more than 2 energy levels. This is this is how it works for 3, and you might also have a 4th energy level, and you might have 4 over here. Any atom system which have more than 2 energy levels will work for laser. Okay, 4, 5, and you have no limit in the upper number of upper energy levels, but you have a lower limit. You must have at least 3 energy levels. At least you must have 3 energy levels in order to have a population inversion, and the population inversion is the must condition for the laser to work. Okay, so and I think I should stop over here and continue next week. That's enough for today. What you have learned on this week is that in order to have a working laser out of your amplifier must have more than 2 energy levels. First of all, you must have a stimulated emission process, and you know what is stimulated emission in compared to spontaneous emission. Spontaneous emission never produces lasing light, because spontaneous emission, the created photons will go anywhere in any direction. But for laser always have this lasing light propagated in only one direction. So in order to create a laser light or a light source which always goes collimated in one direction, you must have stimulated emission. Spontaneous emission will not produce collimated light. Only stimulated emission will produce collimated light. And in order to have stimulated emission working for laser, you must have at least 3 energy levels. Why? Because you must have a population inversion, and the population inversion will never occur for a 2-level system, for a 2-level energy system. So that's why you must have more than 2 levels, at least 3 levels. And what you see over here is how this lasing action work for a 3-level laser. And that's it. Okay, this is, you see, this condition for the stimulated emission, right? N2 and 3 must be larger than N2, so this is a positive quantity always. And in order to have a gain, your gain must be a positive quantity. If this is N2 is larger than N3, then you have negative, and negative gain means you have absorber. Okay. All right, so this is it. Let's stop here for this week, and we will continue next week. Bu hafta size şey vereceğim demiştim, bir midterm take home exam. Şu konuyu da anlatayım dedim. Ondan sonra vereyim. Önümüzdeki günlerde, birkaç gün içerisinde, önümüzdeki haftaya kadar size bir take home midterm vereceğim. Bir haftalık süreniz olacak. Bu bir hafta süresi içerisinde bugüne kadar anlattığım konulardan işte sorular. Geniş bir zamanda yapıp bana gönderebilirsiniz. Evet, bugünlük bu kadar arkadaşlar. Haftaya yine aynı saatte 10.30'da devam edeceğiz. Haftaya görüşmek üzere. Hepinize sağlıklı günler diliyorum.